Forever hold your peace.
I am recording now.
Okay. We are the Murray Amateur Radio Club, August 6th, and we are going to talk about grounding. So I'm going to share my screen. Can everybody see my screen?
Yep.
Yes.
Okay. Let me turn this sucker on. Okay, so I'm assuming you just muted everybody. Is that correct, Jen?
I muted myself. I can mute everybody.
Oh, okay. No, that's okay. If you have any questions during all this, please speak up. So we'll continue here. So the presentation: ground versus grounding versus grounded versus bonding. You've probably heard at least one or two of those words, and there seems to be a lot of confusion amongst this, including in the ham radio world. I can't believe how many people kind of don't really understand most of what we're going to be talking about today. So we're going to, first of all, get rid of some myths. So myth number one: grounding or earthing provides the path necessary to clear a ground fault. That, of course, is not true. In order to clear a ground fault, you have to have a clear ground fault path. So that's myth number one. Myth number two: current takes the path of least resistance to ground. You've probably heard of that before. Actually, no. Current leaves the source and returns to the source, period. End of story. Current is always looking for a way to get back to the source. Sometimes it's not the path of least resistance. Myth number three: grounding brings everything to zero potential. This reduces touch and step voltage to a safe value. Actually, bonding brings equipment to like potential. Grounding provides a zero potential reference. Myth number four: more grounding, the better. Well, that all depends on the National Electrical Code. There's sometimes that's not the case. Myth number five: equipment grounding protects me from lightning. That is not true. Equipment grounding does not protect you from lightning damage. Sorry to bust your bubble. To begin with, we're going to talk about electrical safety. And anytime we talk about grounding, this is something that we always bring up. It's all about safety, your people in the room with you, and the safety of your equipment. PPE should be used at all times. There's a left-hand rule. If you talk to an electrician and ask them what the left-hand rule is, they'll tell you this. It's widely known. It's you actually are supposed to keep your left hand in your pocket, because that's typically where your wedding band and your watch is, and work on your right hand, on the right hand. The way around that is to, and many electricians do, most of these electricians don't wear wedding rings or watches or bracelets or anything like that. You'll be amazed at how quickly your hand can pop off if you are between two active buses. And plus, it only takes about 50 microamps to begin heart defibrillation. So you want to be safe.
I have an anecdote about your left-hand rule there.
Yeah,
Dan,
go
if
ahead.
you like. So my dad was in the United States Air Force for many, many years. As a senior NCO, he worked on electronic countermeasures equipment, so radars and radar jamming equipment. And they had in their shop a giant Faraday cage environment where they could take their equipment in and run it and test it. And they had a little basket outside of that cage that you were supposed to put your rings, watches, pens, change, keys, anything else that you happen to have in your pockets in that basket before you went into this cage. And I asked him one time about that, and he said, well, we had a guy who didn't take his ring off one time, and he was working on some energized anti-radar equipment and put his hand in front of the transmitting horn, and it energized his ring and burned his finger right off. And so he said, we are very, very careful about safety, and we're very careful about that. So I just wanted to share that as an anecdote. It does happen if you're fooling with electricity at high voltages, and particularly radio frequency stuff as well. So
thank you, Jan. It is, you only make that mistake once, and so many times people lose their lives for not being careful. Like I said earlier, it takes only 50 microamps. That's how much is a microamp, guys? This is a test
1/1000th of an amp.
1/1000th of an amp. So 50 thousandths of an amp to begin heart defibrillation. That's not much.
No, sorry, that's wrong. That's milliamps. A microamp is a millionth of an amp, right?
That is correct. Milliamps, microamps. Yes, thank you. Okay. Another electrical safety first tip is always test for voltage. Don't assume there's no voltage in the line. I have lots of experience with that one. And even a 12-volt DC power supply has enough available short circuit current to electrocute a human. So I tell you what, if you are sloppy with electrical, it can grab you. So grounding and bonding definitions, this is something we need to understand. Getting the current away from your equipment and keeping everything at the same voltage potential. That is what it's all about. AC, or electrical system grounding, protects the station equipment from the impacts of overload and short circuits. Bonding protects people from the hazards of electrical shock and electrocution. You don't want a potential difference between two non-current carrying devices. That's why you bond everything together. Earthing is another name for grounding, provides a means of establishing a common voltage reference for both the protection of the equipment and the people. Lightning protection grounding has nothing to do with earthing. Let's make sure we understand that. Lightning protection grounding protects structures, station equipment, and people from damage, fire, shock associated with lightning-induced energy. RF management, RF grounding, which is a myth, protects equipment and people from the high frequency energy induced from a radio transmitter by ensuring all station equipment is at the same voltage level. People with grounding issues, RF grounding issues within their shack, they'll sometimes go ahead and transmit their key up their mic, and they can get shocked if they get the RF coming back at them. And we're going to talk about that. So continuing on, rest of the outline will discuss the differences between grounded, grounding, and bonding. AC/DC ground versus RF ground. We're going to ask the question, why ground to begin with? We're going to talk about lightning. We're going to talk about RF issues. And we're going to talk about lightning protection in the shack, as well as RF grounding in the shack and antenna grounding. We have lots to cover. Again, if you have questions, speak up. So, the grounded conductor is the power return, intended as a current return path from the load back to the source to complete the circuit. Okay, this is the neutral wire. This is the wire with the white or gray uh, color on it. It is not the green wire or the bare wire. The grounding conductor is the safety ground, which serves as an emergency current path that the current will travel on in case there's a circuit fault or over voltage. It too is grounded at the service entrance. It's also connected to metal surfaces and parts along the circuit, grounding them. And the ground in all cases is Mother Earth, sometimes called earth or earthing. So here is a example of a grounding wire, the middle column there. Everybody has seen those. It's the green wire or the bare wire. And sometimes you'll see the green and yellow striped wire. That's all grounding wire. Grounded wire is the, if we were talking AC/DC, it would be the negative, actually the positive on where the electrons are trying to return to the source. That's the grounded wire versus the grounding. Okay. So AC/DC ground versus RF ground. AC/DC ground is used to create a zero voltage reference point, and that's true with both environments, AC or DC. It provides a return path, and it also says for stability and safety. The stability requires a path back. That's the negative piece of it. And the safety, AC circuits require a grounded and grounding path. RF ground, although the symbol is identical to the AC/DC ground, that's where the similarities end. This is required only for certain types of antennas, ones which require current flow to ground to complete the antenna. An example is a quarter wave vertical. Verticals are usually they usually require a ground, and it's a series of radials that go along the ground to complete the other half of the antenna. If you use a complete antenna like a dipole or a ground plane antenna, you do not need an RF ground. And you can think of it of the rowboat analogy. So if you're in a body of water in a small fishing boat or canoe, and if you stand up and push off from the boat, what will happen? Well, obviously the boat will go in the opposite direction of where you want to go, and you will end up in the water. Why? Well, the action produced by your legs pushes against the boat where there is no resistance. Consequently, Newton's law takes over, where there's a equal and opposite reaction. So how is that relevant to RF grounding? A complete antenna system is like a boat on solid ground. An antenna that requires an RF ground, in other words, the other side of the antenna, is like the boat in water. So a complete antenna, example, the dipole or ground plane, is like having that boat on solid ground. It is able to push the RF signals out from it without any need for the ground. The verticals, however, require that other end of the antenna. And so anyway, that's how I think of a complete antenna system versus an antenna system that requires a ground to complete the antenna. As a matter of fact, what completes the antenna on your magnetic antenna on your car? The answer is
Roof.
the roof, or the metal structure of your vehicle or motorcycle. So that's what that's all about. So the question then comes up is, why ground? In the AC circuit, without a ground, you will have no low impedance back to ground. Therefore, you will provide the ground. You will also, you must maintain a 0 volt reference. It's also used in some aspects as lightning protection. We'll talk about that. And is it part of the antenna system? We'll continue with that discussion also. So let's talk a little bit about lightning. And by the way, all of this lightning information was originally presented and created by Dr. Monty Bateman from NASA. I was where was it? It was the Huntsville Hamfest in Alabama, and he presented there. If you know anything about Hamfest, you'll know that Dayton is, of course, the biggest one, but what's the name of the town I just said? Holy moly. Huntsville, Alabama, that is like the second or third largest Hamfest in the nation. So a lot of people were there. Dr. Bateman was there. He worked for NASA. He was in charge of keeping lightning out of the space shuttle, the launching pad. And so he gave a great presentation on how that was accomplished. And he kind of knows a little bit about lightning. And of course, his first slide in his deck was this right here. Lightning is unpredictable. It will do what it wants to do when it wants to do it. Turns out Mother Nature always wins. There is no guarantee. You use this information at your own risk. And even if you follow the advice presented here, I cannot be held responsible for any damage or loss caused by lightning. How's that? So, rule number 1 for lightning. Lightning cannot be prevented, eliminated, or controlled. If you forget about everything, remember this: lightning cannot be prevented, eliminated, or controlled. That is rule number 1. Again, it is unpredictable. It will do what it wants to do when it wants to do it. And look at this picture. This was a picture that I took coming back from Chaco Canyon trip in New Mexico. We stopped at the Maverick in Lehigh, and I took this picture. Talk about a lightning bolt coming down. So let's talk about lightning protection. We know all about how unpredictable lightning is. Let's talk about lightning protection. Most importantly, education is the best protection you can get for lightning. ARRL has lots of good information. If you look at the QST articles, there's tons of stuff to read on. The things that are brought out time and time again is common sense, follow accepted practices, installation should be done carefully, and regular maintenance. That's the thing that most people forget right there, regular maintenance. So the first thing that we are taught to do is catalog what needs protecting. Every device that you have in your shack needs to be identified, and you need to decide how it is protected, not only from lightning, but from the other things that you need to be grounded for and bonded. So this was an example, and this is what I did. This is what's in my shack right now. And heck, if I can do it, anybody can do it. What this allows you to do is to go through and make sure that everything coming into your house that penetrates this wall right here. Can everybody see my cursor? Jen, can you see the cursor?
I do not see your cursor. Yeah, there it is. I see it now.
Okay. So this red box represents my physical boundary, and anything outside of that goes outside of my office. And so whether that is to a grounding rod outside my window here, coax going up to my antennas, or into my electrical panel, everything is identified. And so I can tell from this diagram how this grounding takes place. As a matter of fact, and we're going to talk about this, you can see all my radios here. Each one of them are grounded to a grounding bus, and then that grounding bus goes to a couple of grounding rods outside. So we're going to talk more about that. But anyway, this is the first step that you need to do, is catalog what needs protecting. If you don't do it, if you forget something right here, for example, and a lightning hits you, let's say you forgot about the telephone switch, and I don't have any telephone lines coming into my office, so I don't have that. But let's say you do, and you don't have that yourself protected with that. Well, that could be the source of entrance where a lightning would come and damage some other stuff. So it's important to catalog everything that you have. There's something else that we need to talk about, and that's risk management. There's a balance that you have to take with the amount of cost and effort you're going to do with what you're able to protect. So this is what this slide talks about. The protection plan: intercept lightning with air terminals. We're going to talk about that. Direct lightning current to earth in a controlled manner using the 8-foot grounding rods. Dissipating lightning current in earth, suppressing induced transients with suppression devices. Outdoor equipment exposed to the primary energy of lightning strikes can be difficult to protect without interfering with the operation of what you're trying to protect. Indoor equipment is exposed to secondary energy of lightning strikes and is relatively easy to protect. Again, you start off by that catalog diagram that I showed, and you go and start protecting each one of those entrances, if you will. So here's the risk management part. You need to balance the cost and effort involved in providing lightning protection against that to repair or replace potentially damaged equipment. If I'm spending $10,000 to protect a $3,000 ham radio, I'm kind of skewed with my risk management. It would be easier for me to have the lightning happen and have me replace the radio. So that's what I mean by balancing the cost and effort to provide lightning protection. Everybody can do something to protect themselves from lightning. Okay, you don't have to spend $10,000. You start with the basics, and we're going to talk about that. So let's first talk about how lightning occurs. Lightning is a very interesting animal. The first thing that happens is what's called a stepped leader. A stepped leader is it looks like an earthworm, albeit 20 million volts, that is finding its way to Earth, okay? There's also these things called streamers that come up from the ground, and you'll actually see those. And what happens is when you get a streamer that touches the stepped leader, that's when the circuit is completed and you get a return stroke off of it. You notice that the streamer from the ground, from the house there, is no longer there. All of the energy goes through the return stroke there. So this is a picture of a couple of stepped leaders or streamers that are going up, which if you Google images of this, you'll see this happens all the time. As a matter of fact, every lightning strike it happens. It's just not as bright as the actual lightning. Once the connection is made, obviously there's another leader that made connection with the stepped leader, and the lightning bolt happens, which also is a reason why you don't stand underneath of a tree during lightning storms. You could get zapped. So here's a slow motion detail of the leader looking for ground. And I think this is pretty incredible.
Show the step leader making a connection with the ground. The entire charge then drains from the cloud above.
That was pretty cool, huh?
Show the step leader making a connection with the ground. The entire charge then drains from the cloud above.
What you didn't see is the streamer that actually made that connection.
Show the step leader.
Okay, so let's talk about another type of hazard, and that is static charging. Now, this is where people sometimes get confused. You see these little grounding places to put a grounding connection to. This is to take care of static charging, as in wind static, and not lightning. This is not lightning protection, so don't confuse the two. This is a question for everybody. What is wind static or static charging? What is that? Does anybody know?
So I think it says the wind blows across an object, it drags off some of the electrons and puts a positive charge on that object, because the electrons are kind of floating around in a cloud. They're like always moving, right? And so as the wind comes by, some of them go with it and leave a positive charge behind.
Isn't it the same as trying to get a charge on a fabric and zapping your little baby on the carpet or something like that? It's the same thing, isn't it? Just static buildup?
Yes, static buildup. Static buildup happens by friction. Whether that friction is from the wind against the antenna or your feet rubbing on the carpet, and then consequently hitting your baby with it. Yes, same type of thing.
Remind me not to have Ragnar watch any babies.
So this is why on these antenna switches, you always see a place for a connection to ground. And some people think that they're protecting their antenna in some magical method from lightning. No, that is just taking care of the static charge. Okay. So we have nearby lightning is another type of hazard. There's a couple of things that you can put for nearby lightning. These transorb devices, they, as you can see, they're not for RF. That keeps induced voltages off the equipment. A spark gap is very popular, and you can see how the spark gap works during a lightning induction. Again, nearby lightning. This represents the center conductor right here. It will spark across this area here into this little pod that will then bleed off to ground. It will protect your equipment, especially your center conductor on your coax. Then you have the MOVs that are very popular in not power supplies, but you do see them in power supplies. I'm thinking power strips. Let's see, near miss. Okay, a near miss lightning also is an unsuccessful leader that doesn't make contact to the other side of it coming down. That's can be just as hazardous. Let's take a look at examples of antenna grounding on a tower. You can see this tower is laying on its side, and you can see that right from the antenna, you have these spark gap items where the coax screws into there, and you don't see the coax on this side. But this whole thing is grounded to the tower and then down at the base. Here's the base of that. Down at the bottom of the tower, there's also a set of these spark gap arresters, if you will. Again, it's trying to keep the lightning strike or the near miss away from you. And you'll learn that using straps like this is very much more effective than using wires. You want something flat, as a matter of fact, when you are doing this type of thing. Here's a single point of entry before you get to the house, and this is inside the house. A lot of people will put a copper sheet and mount their lightning protection on there, and then that of course gets tied to outside. Here's a commercial hardline entry point. You can see that there's no thick cables here. It is flat conductors here. Why do we see a lot of this? Why is it flat and they don't use like heavy gauge cables? What's the properties of electricity that make this a better choice? Anybody have any idea?
Electricity goes around the outside of a cable, and just like it goes on the total surface of the flat bars you got, so it disperses easier.
Exactly. Anytime you're pushing current through a wire, the electrons actually ride on the outside of the conductor. So if you flatten that out, it becomes very efficient for that process to happen. So that's why you see, and they don't have to be thick. These are pretty thin, as a matter of fact, 14 gauge or less. But it is copper, and this is the thing that really works. So going to tower grounding. Whoop, page up. I already did that.
Going back to ground straps.
Page up. Yes, go ahead.
The cars before World War II or before the 50s, they used ground straps between the body and the frame. And if you didn't have that, you couldn't get the AM radios in your vehicle to work at all. So that's why they used a lot of those. That's how they hooked it up. Yeah.
As a matter of fact, you'll see a lot in the cars now. Look for your grounding, and I'll bet you'll see that they are using grounding straps instead of cables. When I RF grounded my van, it was all straps. Seems to work better that way. Okay, so for those of you who are going to put up a tower in the near future, and whether or not you're doing it, this kind of goes to show what you're trying to do with with lightning and with close lightning strikes. The idea is to keep the lightning current away from the house. So you do that by putting these ground rods, and you can see how they are moving away from the tower. This is, oh, and by the way, you're also burying these connections between the ground rods. So you want as much surface as you can touching the ground, and that's how you do that. So you want to pull things away from the house. Now the NEC has their own method, or their own requirements, which is the Bible for electrical grounding, whether it's lightning protection or anything else. If you go by the NEC, you'll be okay. But one thing that they do, or they don't suggest, they require, is they have these grounding rods that tie the tower to the building grounding system. Okay, everything is tied together, and there's some of the things that you read in the NEC. We've talked about that. The other type of hazard is a direct strike, and this is pretty interesting. This guy was hit 3 times. He got up. I only put one small clip of it. He got up, walked another few feet, and he was hit again. The third time he got up a third time, and it hit him again, and he did not get up again. But I didn't want to show that part. There's also vehicle strikes, and if you think your rubber tires will protect you, that'll put a crimp in your day. So how do you battle a direct strike? Well, you do it by using Franklin rods. For an extra credit point, what is a Franklin rod? Anybody?
A lightning rod.
A lightning rod. A Franklin rod is an air terminal, aka lightning rod. You install the air terminal at various locations around your house or ham shack, or you should. There's various lengths. Make sure that if you do that, you, oh, by the way, you can create your own lightning rod, and by using those 8-foot or longer rods, the copper rods that you put in the ground, and you just cut them off at various lengths. But here's the important thing. Make sure that you use a blunt rounded end versus a sharp pointed end. And we're going to talk about why. There's the question, why? Well, you have what's called St. Elmo's fire, a corona. And I don't know if you can see that on the screen here, but in the presence of the strong electrical field, air will ionize. It will actually glow a blue purplish. Sharp pointed conductors focus the field and enhance the effect. That is why you have a rounded tip at the end of your air terminal. What else has a rounded tip at the end?
Humans.
Humans, okay, yeah. Wrong answer, though. How about every antenna that you see on a car, your AM/FM radio antenna? You wonder why they put that ball at the end? It's because of this right here. It is the best. It's a place that static electricity happens all the time, and you're traveling 90 miles an hour down the road, and that causes a lot of friction, and it induces static. And so this is why you have that at the end of your antenna. How about your ham radio antennas? The metallic ones will have something bulbous at the end of the antenna. It will never be a pointed end. And this is the reason why. So there's very few things that you can do to really protect your antenna tower with a direct strike. Once you get a direct strike, there is so much current and voltage there, it will vaporize anything that you do. So you have to take that into consideration. The things that we try to do are protect it from non-direct strike events. Okay, this is why you put a uh, this flexible waveguard, 48-inch waveguard between. This is assuming you're on a rotor here, so you want to make sure you continue on your lightning protection past the rotor. So that's just this diagram here. Okay, what about lightning rods for my house? What's the zone of protection? There is a science built around this, and I don't even want to get into it, but basically, kind of like a 60,000 foot level view of this. The reason why you want to put lightning rods around your house is it will kind of creates a sphere of protection. And when I say that, I'm putting air quotes around there, because you have to know how to do it. Something is better than nothing, however. Basically, what this Turkish Journal of Electrical Engineering and Computer Sciences research article says is that the zone protection that see this circle, if you can create a sphere out of that, that is based on the height of the lightning rod, the composition and structure of the lightning rod, and the charge distribution of the downward leader, the stepped leader. And you'll see houses with lightning rods on either side. You'll see barns with lightning rods. You'll see buildings with lightning rods every 100 feet. What they're trying to do is they're trying to create this protection zone that, to make, in layman's terms, if you can prevent as much as possible the stepped leaders and the what's the other one? The other word? Yeah, the stepped leader. Man, I got it. Streamer. Thank you, streamer. If you can keep those from happening, then more than likely you will not get a direct strike. So that's why you put the lightning rods there. Okay, it helps pull the static charge away from that area, so you're less conductive, if you will, and it takes it down to ground as much as possible.
I think they referred to that as the decreasing the potential between the positive and negative.
Yes, exactly. And
so that's how you stream off the static, as it's accumulating in your positive or negative direction. Yeah.
So perfect, Ragnar. That I couldn't have said it better. That's exactly what is going on. And again, what's rule number one? Lightning will do what it wants to do when it wants to do it. So you could be, like I say, you could have lightning rods all over the house, and you could get a direct strike because Mother Nature wanted it. So you gotta mitigate the cost versus what you're going to lose with that. Anyway, so What about lightning rods for my house? What works? Always read, well, this National Fire Protection Association standard. I actually read that publication. Quite interesting. Franklin rods, which are the air terminals, or lightning rods, they work if they're installed correctly and they're maintained regularly. Polyphaser Polyphaser is a company that makes these spark gap arresters. Very good source to learn about how to protect yourself from lightning. What is not recommended and what does not work are the lightning eliminators, lightning preventers, dissipation arrays, early streamer emitters. Um, they are gimmicky, and at best, well, the worst part is they give you a false sense of security. Do not rely on that. Rely on the stuff that works. Okay, so what's your grounding plan? You want to bury conductors to spread out the lightning current. You want to add radials to direct ground lightning current away from the structures and people. You want to tile grounds together, the tower utility perimeter building, or the building perimeter. And this is a simple way of protecting your house. Everything needs to be bonded together. This is actually a diagram of putting multiple, not only multiple earth terminals, but multiple radials on there. And you can look at that at your leisure. Okay, so now let's talk about RF grounding for antennas. You need to ground your antennas, but what does that really mean? Is this what it means? What's wrong with this picture? Anybody see what's wrong with the picture?
The shield on the cable is not connected to anything, right? Or it's not.
The shield on the on this coax?
Yeah. Well, I was looking
it's
at
actually it's actually tied. This is the driver element right here. What else is tied to the driver elements?
It looks like he's got it tied to his lightning rod.
That's right. This is not how you RF ground your antenna.
Wouldn't all your RF go right into the ground? I mean, that's.
You just really messed up the length here, because now you have one leg of this going however long this is, right? Your SWR is going to be horrible. So yeah, this is not RF grounding. Okay, use grounded antennas appropriately. The ground looks like a DC, a short at DC. Loop antennas are great for doing that. Let's go back to NASA. This is the very end of this presentation here. How do they deal with the lightning? Well, you can't see it probably, but they have these catenary wires that completely surround the launch pad. And this is an actual lightning strike that was happening, but there's actually there's one of those poles that actually have the Canterbury wires on there, and they surround the liftoff pad there, which I think is pretty interesting. You can download his presentation by going to this website here. Let's see, lightninganswers.com. Going to lightninganswers.com, you can go ahead and sign up, register, and he will allow you to download his presentation. The ARRL website also has a great multiple articles on lightning protection. So There you go. Lots of information, lots of things you got to kind of remember. But if you take it one step at a time and start protecting the stuff that I try to do things the least amount of money possible that will give me the most bang for my buck. Okay. That's how I do everything in my ham shack. And it works with lightning protection as well. I don't have 15 ground rods. I only have 2. And when I put up my tower, I'm going to put 4 more grounding rods. And everything already is grounded or bonded to the grid. We didn't talk about ground loops for your equipment. That's something that you learn in the technician class on how to prevent ground loops. So just do things by the book, and more than likely you'll be safe. And of course, this is no statement of guarantees, because lightning will do what it wants to do when it wants to do it. Mother Nature always wins. The best we can do is try to mitigate that, and to, if the lightning does happen, to get it away from your property, from your person, from your equipment, and out into the ground.
So Dan, do you know anything about EMP protection?
Oh yeah, that's another presentation.
So I know, we talk about our emergency preparedness, and if people don't know what an EMP is, it's an electromagnetic pulse. And the typical cause of it would be a high altitude nuclear burst. So could be a terrorist attack, or could be a war situation. That burst will take out pretty much any electronics that you happen to have laying around that isn't shielded. But I know that there are ways to shield your equipment even when it's connected and operating. I know I read a book on it. That was a military document that talked about EMP shielding and how to shield your feed lines and things like that. And I was just wondering if that was something that would be relevant to the lightning and grounding discussion.
You see, here's the problem with EMP, and I'm going to put CME on in the same realm, the coronal mass ejection. As a matter of fact, that is more apt to happen than an EMP will, but you don't discount either of them. The last time a CME happened was 1859, I believe, the Carrington event, and it did the same type of thing. The sun blasted out a huge burst of radiation, and back then in 1859, and I could have the year messed up, but I think that's right. We had lots of telegraph lines that acted as antennas for this induced current, and there were fires that happened all over the place. The telegraph system was going crazy. People were getting shocked. And that was just with the telegraph system. Can you imagine the same Carrington event happening today? It would be, as a matter of fact, an EMP has 3 main pulses, talking about EMPs. The first pulse happens within billionths of a second. That is the pulse that wipes out the computer chips, okay? That's where you have 50,000 volts per square meter that is induced in your electronics. This is why things are fried. This is why, if you don't do it right, and you have to do it right, and there's a way to do it, and doing it right is not using your microwave to protect your ham radio. Doing it right is a whole other ball of wax there. So you have that primary surge that happens within billionths of a second. Then you have the secondary surge and the third part of the EMP wave, which can last from a few milliseconds to many, many minutes. And it is that the Carrington event type of surge happens. It's the same type of uh, induced voltage that this is where the power lines will become antennae uh, for that part of the HEMP, the high altitude blast. The best protection is to unplug things. Get yourself off the electrical grid. You have long cables. Anything that is out is an antenna, and if you keep that small, then the CME type of events or the last part of an EMP, you can protect against that. As a matter of fact, some surge protectors will protect against CME type of stuff. Okay, surge protectors are too slow for the billionths of a second that it requires to fry your electronics. Although they have technology now that's not so true anymore, thank goodness. So to make a long story short, the HEMP, the high altitude explosion that you're talking about that produces an EMP, completely different from lightning grounding and RF grounding. Two different subjects altogether. You have to deal with them in different ways. The thing, as a matter of fact, even the CME, the coronal mass ejection event, having all of these grounding wires works not to your benefit, because you want to cut all of the antennas out of your system. So if I have a perimeter around my house, that is one big antenna with a CME event. Okay, so there's ways that they use to mitigate that stuff, and these are real life disconnects. But fortunately, with the CME, we have time. Generally, we'll know NASA is monitoring the sun 24/7. And so they will know. As a matter of fact, we just recently had, within the last few years, a close call with the CME. It took out half the East Coast and Canada when that happened. And that was, we just barely hit the corner of what could have happened. If it was a direct hit into the earth, there's going to be a lot of unhappy people that is there. And if you're not plugged in, chances are your equipment will be okay. It does not fry anything. The EMP is another story altogether. So I have a presentation I did for Salt Lake County ARES on EMPs. And maybe if anybody's interested, we can do that sometime.
I'd be interested in seeing that for one of our advanced topics classes.
Yeah, sure.
I think that would be a good one to talk about, because there's also like a relatively near star going nova could cause a similar type of event, right? So it's not like it has to be a nuclear war that's doing it, or a terrorist action or something like that, but there are things that could cause this kind of damage, and we should be thinking about it and prepared for it.
So what should you unplug if our sun goes supernova?
If our sun goes supernova, just unplug your life, because you got about 8 minutes.
You got 8 minutes to think about it.
There's actually a science fiction story called Inconstant Moon, and they made it into a Twilight Zone episode, I believe, where this guy notices that the moon is much, much brighter than it should be, and he realizes that something bad has happened to the sun on the other side of the earth. Right. And So you pretty much have until morning, and so he has a big party, and you know, because what else are you gonna do? What can you do about it? You know, there's not much you can do. So,
As a matter of fact, has anybody seen the movie Knowing?
no.
Yes.
That is a great,
Beautiful.
yeah, that is a great example of a of the sun doing a super CME that just blew the complete atmosphere off the Earth, and it completely took out the Earth. The story is aliens came down to pick up select children, but it's actually a very good movie. I really enjoyed it. But the special effects they had when at the very end, a spoiler alert, was actually fantastic. And I can see, you could see the sun, the destruction just going 6,000 miles an hour, just boom, just going just taking New York City out, and it was actually very interesting. That's what would happen in a direct hyper CME event, and in which case, yeah, you know, I haven't started drinking. Maybe I'll start drinking then, and have one hell of a party.
Yeah. Not much else you can do in that
not,
case.
not much else you can do. Yeah.
All right, I'm going to stop recording,
Oh, were we recording?
Oh, cool.
and we will wrap